Okay, great. So I posted homework 3. Homework 3, the homeworks are continually ramping up in difficulty. So with homework 3, it's fairly long. Well, I don't know. See, I look at the problems and I'm like, oh, these are easy. I can answer these in like 1 or 2 lines of code. So anyway, this is a little, okay, anyway. So get started on homework 3. Please do your best to solve all of the problems on your own first, okay? Solve all of them and do them. There's a few challenge problems in there, and I've taken them straight from the textbook. And so there's a section where they have what they call these car talk puzzles. There's a radio show called Car Talk, and every now and then they have these little puzzles on there. And they're usually like little word puzzles, like, you know, what kind of word can you make that has this pattern and stuff like that. And then, and you're also provided with a list of words, and you can kind of search the list of words for possible solutions to these puzzles. And they're kind of fun, but they're also kind of hard. You got to kind of think through them. So anyway, I encourage you to get started, start thinking about those puzzles. And a lot of times, because this is how it often goes, is, you know, at work, you're going to have to think about puzzles or think about these problems, and you have to sit and do problem solving. And it's really, it's a part of your brain that needs exercise, just like any other aspect of the body and things like that. And so I really want to encourage you to do that, and try to avoid looking at the solutions. The solutions are available. You can click the link in the textbook and it will show you the solutions. And certainly you can look at them, but you're going to lose out. You're going to lose out on that problem solving experience. And so, you know, my encouragement is, if you're totally stuck and you can't think about it, you know, think about it, but then set it aside, work on something else. And then, you know, as you go about your day, just keep it in the back of your mind, and the solution might come to you. It's rather surprising how the brain works, and that sometimes at unexpected moments, the solution will come to you. You know, if you find yourself like truly stuck, the solution is not coming to you, you know, and you find yourself really tempted to look at these solutions, okay? Again, my encouragement is don't look at the solutions. But if you are going to look at the solutions, if you're going to do it, then at least do it in a way that's not detrimental to your learning. And what I say is, you can look at the solution and you will get a sense of how to approach the problem. Okay, you can read it and you can say, oh, this is how we solve the problem. And then don't immediately code it up. Close the solution and then kind of tell yourself, I'm going to write the code tomorrow. And then that way you can have the solution in mind, but you won't have the actual code. And so at least you'll exercise the brain in the way of like, I know how to approach the problem, but then your brain has to think about how to go about coding it, okay? And so at least you'll get some experience coding. Yeah, but as far as programming goes, a lot of these things, you know, programming is very little typing, a lot of just sitting and thinking about how do I go about solving these problems. And I think the textbook that has some really, you know, really good puzzles that are available to you in terms of at an appropriate level of difficulty. So anyway, take a look at homework 3 there. I've also posted this questionnaire, remote teaching questionnaire. It's anonymous. This was kind of encouraged by the Office of Instructional Development or something like that, to try to get feedback on how remote teaching is going. I think almost all of us prefer real life teaching rather than remote teaching, but unfortunately, given the situation that we're in, that's not a possibility. And so, as far as how remote teaching goes, and if there's anything we can do to make it better for you, or whatnot, let us know, and let me know in the questionnaire. It's anonymous, but it's helpful. So, okay. I also posted the syllabus, and I'm embarrassed that it's coming so late. And ultimately, I decided no midterm exam. Okay, so this is what we're gonna do. I had, you guys are getting the class on easy mode because it's remote, and the homework assignments I'm putting at 40%, which is probably a little bit too heavy considering that the solutions are already out there. So, whatever, that's just, it'll probably be a little bit harder in future iterations. Please, so anyway, keep that in mind. I'm not expecting anyone to write a brew and walk review, but if you do make a brew and walk review, my request is that you don't advertise this as like easy mode class. It was so easy, okay? I'm doing this because I'm taking into account that it's being remote. It sucks for everyone. So we're, this is how I'm doing it now. I don't expect to do this in the future when we have real life in-person classes and stuff. So I, don't fill up brew and walk and say like, oh, this class was so easy. And then because, in the future, students will be like, hey, I read on brew and walk that it was so easy. And now it's like, not as easy. So anyway, that's all I have to say about that. But yeah, okay. Anyway, you guys are getting easy mode. I think maybe you can, in the survey, if you find out this is not easy mode and like my idea of easy mode is actually not easy at all, let me know, and just let me know that I'm out of touch with reality, and I'll be like, okay, I need to make adjustments here. But this is what we have. Okay, I've decided to go to Numpy. Numpy is not covered in the Think Python textbook. Numpy is not part of what we would call like base Python or the regular Python. So Think Python only covers base Python, and it doesn't cover Numpy. Numpy introduces basically the Numpy Array, which is a data structure that's not part of base Python. And right now we're doing all of this stuff on data structures. We spent time talking about lists and dictionaries and tuples and all of that stuff. And so I thought it would be appropriate to talk about Numpy arrays here. And then we'll go back into Think Python and continue talking about files, classes, and objects and stuff like that. But Numpy is not a base structure. But it's incredibly useful, especially for people working in data. So anyway, this is all coming from the Python Data Science Handbook. This book over here, excellent book. This is what I based my 131 class on. Anyway, you should pick up a copy of this, or I mean, you don't have to buy it. While you are a student at UCLA, take advantage of the online digital library that you have. You guys know about ProQuest, right? ProQuest Safari Books Online? Maybe? Okay, let me show you. You have to VPN. You have to connect to the UCLA VPN, but type in ProQuest.SafariBooksOnline, okay? Your money, your tuition money goes to pay UCLA and part of that money goes to the library, and the library pays for a subscription to Safari Books Online. So, you know, I say it's free access to UCLA students, but technically you have been paying for it. So, but anyway, this gives you access to the entire O'Reilly catalog of books, which is, they're really, really great textbooks for programming. It's probably my favorite publisher for programming textbooks. And so you can look up Python data science, or just type in Python data, okay? And there's going to be the Python data science handbook and Python for data analysis. And these are really good textbooks. You can read them. You got to read them in your browser. That's how they kind of prevent you from distributing a PDF of the entire textbook. But the entire textbook is online, and you can read it here. Okay, it's really great. So make sure you take advantage of this while you are paying your UCLA tuition. Okay, otherwise you got to pay, you know, $50 for each of these books. So ProQuest at Safari Books Online. Okay, anyway, let's introduce NumPy. Okay, so when you use NumPy, you're going to always run this at the top of your notebook. Import NumPy as NP. So if you installed Anaconda, it's already going to have installed NumPy for you. Okay, and you import NumPy as NP, which means you can kind of call any of the NumPy functions by just typing in NP, and this is the convention. If you don't do this, people are going to have a hard time reading your code. There's technically no law, like it's not, it's not going to throw an error if you name it as something else, but it's just going to confuse other people. So you write import NumPy as NP. You can ask what version of NumPy is installed on your machine. I think the latest is 118.3. I should probably go and update that, but you know, this is NumPy. Okay, so what NumPy introduces is the NumPy array. Okay, NumPy arrays are mutable, much like lists. Like lists, they are mutable. The key distinction is that unlike lists, arrays can only contain data of the same data type. So this is a lot like the atomic vector in R, and the atomic vector in R can only contain data of one data type, right? Either integers or floats or something like that. And that's what's going to happen with the NumPy array. And because NumPy arrays will only have one type of data, the underlying code in NumPy has been optimized for rapid element-wise operations. So you can do multiplication and addition and all sorts of stuff very, very, very quickly with NumPy arrays. Okay, you create the array using np.array. All right, so you say numpy.array, and it's going to create an array. So you can put a list using square brackets inside the array, and now you have created a NumPy array. Okay. When you call print on an array, on a NumPy array, it's going to look like this. Okay, it looks like square bracket 1, 2, 3, and you say okay. And you can distinguish that this is an array and not a list, because if you print a list has commas in between the numbers, okay? And arrays do not, okay? A printed array has no commas, and a printed list does have commas. Or if you don't print it out, it's gonna be wrapped in the word array, okay? So this is how you can tell it's an array, because it'll say array, and it will look like this, or it will look just like this if you print it out, all right? So that's how you can tell, is it an array or is it a list? Okay, so if you try to mix different data types into the array, Python or NumPy is going to upcast to the less restrictive type, right? So here I've got 1, 2, 3.0. 3.0 is the float, and that's the least restrictive data type here. Okay, and then I've got some Boolean values. And so it upcasts the Booleans to the false and the true to 0 and 1, and it upcasts the 1 and 2s to floats. Okay, and so we can tell that they are floats because they have decimals or dots after the number to indicate that they are floats. All right. And here, if I put 3 in quotes, then it's a string, and it's going to upcast everything to strings. Okay, and so so that's what we have it. Okay, R calls it coercing, and NumPy it's called upcasting. Has this lecture been pushed to GitHub? Oh, you know what? I'm so sorry, I forgot to do that. Okay, I will go ahead and do that right now. Are here. Let me do this. All right. What's going on? Why is my git status broken? Not broken, but taking forever. Okay, yeah, that's what we want. All right, so git add all of these things, git commit them. 05, it's draft of 0501. And great. Okay, and we're going to go ahead and push all this. Sorry about that. Thank you for the reminder. Let me push all of this. Okay, they should be up now, so you should be able to git fetch and git merge those changes. Okay, so so that's called upcasting. All right. Arrays can also exist in higher dimensions. So so you have, you know, basically so we've been looking at the equivalent of an R vector, but this is just a one-dimensional array. And then the equivalent of an R matrix would be the two-dimensional array, okay? And you can have higher dimensional things, and they're all just called arrays in NumPy, okay? So they're similar to R, but in R you just have the atomic vector. Atomic vector with dimension 2 would be a matrix, and atomic vector with higher dimensions would be the ND array. But in NumPy, they're all just arrays, okay? And so here I've got, notice I have a list of lists, okay? So I have a list of, you know, a list of 3 and another list of 3, and this will, NumPy recognizes this as creating a 2x3 array, okay? So when you print out a multi-dimensional array, the number of opening square brackets is going to be the number of dimensions. And so this array is two-dimensional, okay? If you try to create a multi-dimensional array, but if the dimensions don't match, you're going to get an array of lists, which is not going to be as useful. So here I've created an array with a length 3 list and then a length 2 list. And then, and if I say make an array out of this, I get an array with a list of 1, 2, 3 and a list of 4, 5, which I don't know what we can do with, okay? It's not as useful. Do the lists have to be the same length? Yes, the lists have to be the same length if you want to turn it into a multi-dimensional array. If they are not of the same length, you're going to get this, okay? You're going to get, so it doesn't throw an error, but this is much less useful, okay? Okay, other ways to make arrays, your quick array creation is going to be using the zeros and the ones function. So I think a common thing that, at least an idiom that I use in R is I use like rep 0, you know, 500 or something. Here with NumPy, you just call zeros. np.zeros, and you say 5, and this is going to create an array of length 5. Okay, and by default it does floats. Okay. You can tell it I want integers, okay? You can say data type equals int, and it's going to fill it out with 0 integers, okay? You can also give it a tuple, you know, here I give it a tuple 2, 4, and this is going to create an array with 2 rows and 4 columns, okay? So you can give it dimensions. You can even give it dimensions as a list also. So you give it a list 2, 4, and NumPy is going to make a 2x4 array full of zeros, right? And so here, notice this. This is I give it a 2x3x4, okay? And so this is going to create an array of 3 dimensions. I guess it would be 2 sheets. Each sheet has 3 rows and 4 columns, okay? So I've got 3 rows, 4 columns, and I've got 2 of those. So that's my 2 by 3 by 4, okay? And we can see it's 3-dimensional because the number of opening and closing brackets at the front is, there's 3 opening brackets. All right, and then here, if I go 2, 3, 4, 5, okay, what does this do? This makes 2 blocks. Each block is 3-dimensional. Each block has 3 sheets. Each of those sheets has 4 rows and 5 columns, okay? So I don't know if you can visually see this, but you've got this now, this array that exists in 4-dimensional hyperspace. And you've got, you know, two blocks, each with three layers, 4 columns, or 4 rows and 5 columns. Okay. In addition to zeros, there's ones and full, which can create new matrices. All right. So ones is almost exactly the same thing as zeros, but it's going to insert ones instead of zeros. All right, which can be useful. And then if you need to fill it with some arbitrary value, okay, NP full works the exact same way as zeros and ones, except you provided another value, and that value is going to be the value that populates the array. Okay, so here I just give it the value 1.2 and it fills the array with that. Okay, you can get random numbers. Okay, Python has its own random library, but Numpy comes with random stuff as well. And so all the random generators are going to be np.random.something, okay? So you can set a seed if you need reproducibility, all right? Numpy uses the Mersenne twister. These seeds behave differently than not behave differently, but the seed here is not going to give you the same seed results as R, okay? So you call a seed in R and you call a seed in Numpy, you're going to get different numbers. So don't expect the numbers to be the same. But they behave the same in that as far as random numbers go. Or do I need to explain how a random seed works? So in a computer, random numbers are not truly random, right? Computers follow some kind of instructions. And basically, when we ask the computer for a random number, it's following instructions to produce numbers that behave like random numbers, but they're not actually random, okay? And you can imagine there's kind of like a sequence of numbers that the computer is going to produce, okay? And the seed, and you can think of the sequence of numbers as, you know, following, you know, certain steps. And when you set a seed, you're just basically setting the initial value that it's going to produce, and therefore you're going to have the same starting point. And then because it's following steps, it's going to produce some sequence of numbers. So if the sequence of numbers, you know, maybe is like 5, 6, 2, 4, 8, okay, you can call seed again and you're going to get that same sequence, 5, 6, 2, 4, 8. Whereas, you know, later if you continue it, you're going to get something else. But every time you call seed, it's going to bring you back to that top and you're going to get 5, 6, 2, 4, 8. Okay, that's different from real life, where if you were rolling a die or you know, drawing numbers out of a hat, there's no guarantee that you'll ever see the same sequence of numbers again. But because computers, well, anyway, so this is randomness. So the default, the simplest, is you just call np.randomRandom. There is random in base Python also. Yes, there is a random in base Python, and it's going to produce random numbers kind of into a list. And so a lot of times people prefer the NumPy random because it's going to go into a vector, or not a vector, into a NumPy array, which has computational advantages over numbers that appear in a list. Okay, does setting the seed for NumPy not affect the seed for random and base? Ooh, I think they are separate. I'm not 100% sure, but I'm pretty sure they're separate. Okay, so because it I think. Pretty much every operation that makes use of the random generator will move you down kind of the random track, okay? So here, np.random.random will just produce random uniform, okay? So the random function will produce an array of 5 random uniform values. They come on the interval from 0 to 1, okay? You can call random n, random.randn, and this will produce values from the standard normal distribution, okay? Standard normal distribution meaning mean 0, standard deviation 1. So you're gonna get values like negative 1.1, oh, we got negative 2.3, which is unusual, and things like that. And you can also call np.random.normal, okay? And here you specify the mean. You say, I want a mean of 10 and a standard deviation of 3 and I want the values to be in a 2x4 matrix, okay? And so these are your random normal values here. Okay. So I would say the 2 most important ones are just random, which will give you random on the uniform value, and then random integer, okay? And so here, this says on the interval 0 through 10, okay? Much like slicing, 10 is exclusive. So starting at 0 up to, but not including 10. So that's gonna be the digits 0 through 9, okay? And then here we say we want 20 of them, okay? And so I get this array of 20 values, basically 20 digits, 0 through 9, okay? If you want to simulate dice rolls, okay, you can say from 1 through 6, and you'll get basically 1, 7 will give you the integers 1 through 6. So that's like simulating dice rolls, okay? And then you can always click this. I guess I should update this to 1.18.1, but I don't think it has changed. Oops, I didn't actually want to click it. But that will list off all of the different random generator functions out there. So pretty much all the probability distributions that you can use in R also exist here. So you've got the beta, binomial, chi-squared, Dirichlet, exponential, gamma, geometric gumbel, Laplace, log, whatever, okay? All of those things, right? Okay, you can make sequences, right? So you have the, so in base Python, you have the range object. So we can go from 0 to 10, step size 2, okay? So this is regular old Python. This is not NumPy. And this will give you, 0, 2, 4, 6, 8. Same behavior, but this is a list, right? So a list, this is a list of integers, which is nice, but computationally, if you try to do computational operations with a list of integers, it's slow because the list contains a whole bunch of overhead in that each of these things inside the computer's memory, it says, this is an integer type, this is an integer type, this is an integer type, and it's keeping track of all of that, okay? With the array, it just says the whole thing's integer type, so it's fine, okay? So, so you can do this. This is the A range. I mean, you can do it this way too. You can say make an array out of the range object, and you'll get the same result. But so here's just some examples: 0 through 100, count by 5s. You can just do NP A range 20, and it's going to give you the integers 0 through 19. So that's useful. Okay. So A range will make ranges. Okay. Then you got linspace, linear spaced values. All right, so you just say start here, stop here, and this is how many values I want, and it's going to equally space them out. Okay. So you can say I want 0 through 100. Okay. When you call linspace, it's going to include the last number. Okay. And here you want 11 of these, so this will go 0, 10, 20, 30. Right. A lot of times you have to do n plus 1 as far as what you're thinking. So if you want them spaced out by 10, you go, okay, well, there's 10 numbers from 0 to 100 divided by 10 will give me 10, but then you'll need 11, right? If you do 0, 110, they're all going to get spaced out by 11.1. Oh, first quiz question. Yeah, good. Thank you. D as in dog is the first quiz answer. D as in dog. Okay, so just be careful with using linspace. It's always good to kind of check to make sure you're getting what you want. There's an optional parameter, endpoint. Okay, so you can say endpoint false, and this will not include the endpoint value. Okay. And so here, when you do something like this, you might not get the behavior you want, okay? So when you do 0, 109 endpoint false, the last number is going to depend on the output length, right? So the last number here is 90, and the last number here is 88.88, okay? Whereas when you don't specify endpoint false, the last number is 100 in both cases. Okay, so just be mindful of those settings here. All right. When you create an array, okay, so here I'm creating an array of ones, 3 rows, 4 columns, and you've got a few attributes: number of dimensions, the shape, and the data type. Okay, number of dimensions, it says it's a 2-dimensional array. So you just say, well, X is this thing. X, number of dimensions on X is 2. The shape, so you do X.shape is 3 by 4, 3 rows, 4 columns. And the data type, the numbers in here are floats, okay, 64-bit floats. You can specify, you can say, I want 32-bit floats, which will give you less precision and stuff like that. Those are optional, or integers and things, okay? When you create a 1-dimensional array, right? So here's a range. This would just be a range 12, okay? The number of dimensions here is 1. And take a look at the shape. The shape is a tuple of length 1, okay? This is a 1-dimensional array. This is not 1 by 12. It is a 1-dimensional array, so it only has dimension 12, okay? There's no, it's not 1 by 12 or 12 by 1. It's just 12. Okay, so if you can reshape an array using numpy.reshape. Okay, so you take the array, which is 0 through 12, and you can say, let's reshape it, right? So you can reshape this and say, I want 3 by 4, okay, and it fills it out, okay? Notice when you do this, it fills it out row-wise, which is different from R's behavior. So if you, I think you guys probably did this in R, where you took an array and you applied a dimension attribute and it reshaped it into a matrix, okay? When you do that in R, it fills it out column-wise. For Python, it fills it out row-wise. So that's just some behavior to be aware of, okay? When you do a reshape, though, it leaves the original array unchanged, okay? So this is not going to change J. J is left unchanged, okay? So J is still 0 through 11. Okay. Here I can do j.reshape. Okay, so you can so here notice I called numpy.reshape j. I said reshape, and then I put j in there and I gave it the dimensions. Okay, you can also just call j.reshape. So that's fine. You can do j.reshape, and you'll get in here I do 4,3 and I get 4 by 3. Okay, and again, when you do something like this, this still leaves j unaffected here as well. Okay, so you can call reshape the function, or you can call basically the reshape method from an array. All right, so here is k. This is the result of reshaping j. Okay, and if you transpose k, you can just do k.t, and this is going to be the transpose of k. Right. So transpose is an attribute of k. Okay, and so when you call k, or it's going to return basically the transpose of itself. Okay, so I think this is perfectly expected behavior. Okay, and again, when you call k originally, k is not modified. It's just k.transpose is just an attribute of k itself. Okay, so the neat thing about Numpy arrays is that all of these things return arrays themselves, and so all of the methods or the attributes exist and they can be chained. Okay, so here I'm creating the range, 0, 12, 1, which is basically the digit numbers 0 through 11. Okay, and then I can call reshape to make it a 3 by 4 matrix or 3 by 4 array. And then I can call .t, and that will make it a 4 by 3. Okay, so you can chain them in one line here, which is a nice nice thing that we can do, because each of these operations is returns a Numpy array that has the attributes. Okay, all right. This is very important. When you have a one-dimensional array, the transpose of the one-dimensional array. Okay, so notice there's no there's only one dimension here, so there's no dimension to trade it with. Okay, so if I say transpose this, it still remains a one-dimensional array. Okay, so if I do y.transpose, it's still a one-dimensional array. Okay, it doesn't suddenly become a column. All right. So if you wanted to do something like that, okay, so notice this is a single dimension, right? There's only one bracket here, so this is a one-dimensional array. What you can do is you can take y and reshape it to be a 1 by 12 array, okay? And if I do that, now this is two-dimensional. This is two-dimensional, it's 1 by 12, and we can tell that it's two-dimensional because there's two opening brackets and two closing brackets, okay? So z is going to be a two-dimensional array. Its dimensions are 1 by 12, and now I can transpose this. If I do z.transpose, now I get a column of 0 through 11, okay? And the shape of this is 12 by 1, okay? So so don't mix up, or if you do something like this, you might not get the behavior you want. So just be sure you're doing this, right? Okay. Subsetting and slicing arrays. So this works exactly as we would expect, okay? You can select the fourth element, index 4, right? So matrices or elements are 0 indexed, so 4 is actually the fifth element. So index 4 is 4, the shape is 12, and you can also slice, okay? 4 through 6, so going from the 4th comma to the 6th comma is going to return 2 elements here, okay? So that behaves exactly, right? If you have, you can also give it a step size as far as slicing goes, which exists in base Python as well, okay? So you can go 1 through 8, step size 3, so you get 1, 4, 7. Here you can go make a range 100 and slice to get the even values, okay? Or you could have created the A range using a step size of 2 anyway, okay? You can slice in higher dimensions using a comma, okay? So here, I've got a 3 by 4 array, okay? And so here I'm gonna say I want row index 1, column index 2. So row index 1 is this row. Column index 2 is this column, 2, 6, 10. Okay, so row 1, column index 2 is going to give me back the element 6. Okay, and when you slice the array here, it's going to just return a value that is an integer. It's not returning NumPy. It's returning the integer. It's no longer an array. Okay. Over here, though, okay, you can say here I want to. So here's the original array, and here we're going to ask slice 0 to 2. Okay, so it's going to slice basically the first 2 elements for the rows, this row and this row, and the columns, this column and this column. Okay, so it's going to pull out that top corner 0, 1, 4, 5, 0, 1, 4, and 5. Okay, and this remains an array. Okay, you can just say also give me row index 2, and that's going to give us that, and that's also going to be an array. Okay, and this is, and it, has all the shape attributes that we would expect, right? You can also say, I want the column index 2, and that's going to be 2, 6, 10, and that's also going to have a shape, a one-dimensional shape. Okay, I think the behavior of this is all expected because we see very similar things in R. The important thing is you have to kind of leave it blank. You can't just go 2, nothing. You generally put in a colon here to indicate you want all of those rows there. Okay. Here's an important thing is that when you do a slice like this, though, okay, when you get a slice like this, it is a view object. Okay. So again, so here I have sliced, and so this is just some sub matrix of this matrix. So I'm just slicing this top corner 0, 1, 4, 5. It is a view object, which means it will update dynamically if the original array is updated. Okay, so notice what's going to happen. I'm going to take this top element here, 0, and I'm going to replace it with 99. Okay, so even though I haven't redefined z sub, because it's a view object, it's going to reflect the change that I've made here. Does that make sense? It's much like the dictionary view objects for the keys and the items. The view object gets updated anytime the original element is updated, okay? And we can see that the original element has been updated to 99145, and the view object also reflects that change. Okay. Here, notice what happens though, okay? Over here, I create an entirely new NumPy array, and I assign it to z, okay? So this array has nothing to do with this array, okay? This array has been updated so that the corner takes on the value 99, okay? This array happens to be called z. Over here, in this command, I'm creating an entirely new array, and I just happen to name it z as well, okay? So this array has nothing to do with the old array. And so therefore, the view object doesn't get modified, okay? The view object still points to the object formerly known as z, which unfortunately no longer has a handle, okay? We don't have a handle on that object, right? So it's unfortunate, but this thing will still be this thing, okay? If you want to make a copy, you can do take the view object, all right, and then make a copy of it, okay? And then so this thing is now a copy. This is no longer a view object, okay? So this thing is a copy, will not be modified when we do this. So if I take this top corner and I change it from 0 to 55, the copy, which is not a view object, remains unaffected, okay? And we could see that z itself has been modified, okay? The top corner has been changed to 55. The copy, which is a copy, is unaffected by that change. Is that all right? Okay, that was quite a bit. This is just a very, brief intro to NumPy arrays. I'll probably cover a little bit more on NumPy arrays on Wednesday, and then we'll get back into kind of the textbook flow of things. But I just thought while we're doing a whole bunch of data types and data structures, I thought I would introduce this this data type here, the NumPy array. Okay, are NumPy view objects mutable? So they are view objects. Here, you know what? That's a good question. Let me see. All right, so let's go ahead and make we'll do NumPy a range. Let me give you the second quiz question. Second quiz question is A as an apple. A as an apple. Yeah, so okay, so here let's do a range, and we'll make it 3 by 4, okay? And we'll print z. Oh, shoot. Okay, and then so we'll do we'll call this view, and this will be we'll take the top corner and the top corner. Okay, so here's the view object. Okay, and then, all right, so let's do let's take the top corner of the view object and let's assign 99 to it. Okay, and so if I look at the view object, it looks like this, and if I look at z, z has been modified as well. Okay, so the view object and z are kind of linked, and so when you modify the view object, it also modifies the underlying array. Okay, and so yeah, if you ask for the type on view and the type on z, they're both ND arrays, and so they're gonna both have the same set of methods. Okay, so I can do view.t, and that's going to give me the transpose. Okay, so we can see that's the transpose 99145 becomes 99415. So yes, so you can do, so recall that all of these things return copies, right? So if I reshape this to 4 comma, okay, so this is now a one-dimensional array, but keep in mind, calling transpose and reshape doesn't modify the view object itself, right? So there are certain methods will modify the view object, right? Like if I do view 0, 0, and this is going to be intrinsically linked to the array z, okay? But then other things, like if I reshape it, okay? So if I do so if I take this and let's say I just want index 3, okay, which will be 5. Let me see. Can I set this to -100? What happens here? Yeah. So because this is a copy of the view object. The view object itself is unchanged. So I don't think, so I would have to, I'd have to do something like this. X is this, and then we can do X index 3 is equal to -100, and we can print X. Okay, and so that will change that, but the view object itself, again, unchanged here. Okay. We'll end there, and I don't know if you guys had any questions, but that's it. That's it for today. I guess I can update my my slides and notes with some of this stuff where we played around with the view objects to see how they go. All right, that's it. We'll see you guys on Wednesday.
Can I ask a short question?
Yeah, go for it.
I asked the same thing to the